We're looking at rules and techniques of taking derivatives. And so we're going to learn a new rule today, which is called implicit differentiation. And we use implicit differentiation when we have multiple variables in our equation, and it's hard to solve for one in terms of the other. That is called, that equation, if that's the case, is in implicit form. So in front of you, you should be seeing explicit versus implicit. And let's just talk about that really quickly. So the function can be expressed as an equation in terms of one variable. So if we can get y by itself and express it in terms of x in this case, then this would be an explicit equation. And when we took the derivative of that, we would just go straight forward and do it just how we've been learning. Implicit form is when you have an equation where it's in terms of both x and y in this case on one side of the equation, or sometimes it's both sides of the equation. And in this case, a lot of times an implicit equation cannot be rewritten, or it's very hard or difficult to solve for the variable y in terms of x. And so if we can leave it in this form and learn a rule of taking the derivative, it will make our life so much easier. And so we're going to learn about implicit differentiation today and how to do that. Okay, so I pulled up the chain rule. We need that chain rule in order to understand and to apply implicit differentiation. And so let's just recall and walk through this chain rule really quickly. Chain rule, if we have two functions, f and g, that are both differentiable, and big F could be rewritten as a composition of two functions, f of g, and that's the composite. Then we could write capital F of x, composition of f and g could be rewritten as f of g of x. We can say since f and g are both differentiable, then that composition function, capital F, is also differentiable. And to find that derivative, we looked at the derivative of the outer function of the inner function inside, it stayed the same. And then we took the derivative of that inner function. So we can write things that way, or sometimes it was helpful to write it using Leibniz notation. So if we have y is equal to some f of u, where u is a function of g of x, both f of u and g of x are differentiable, then we can say that the derivative of y with respect to x, dy dx, is equal to the derivative of y with respect to u times the derivative of u with respect to x. And then we had to go back in and rewrite what u was in here. So replace u with g of x. Okay, so that is important to know, that if we have a function here in terms of another function, that we have to look at the derivative of the outside of the inner times the derivative of the inner. So let's look at maybe an example of an implicit equation. So maybe we have, let's say, x squared all over 4 plus y squared all over 9 is equal to 1. So I'm just curiosity, do you guys know what the shape of that graph is by just looking at that equation? And that right there is in implicit form. But we could technically put this in explicit form by getting y all by itself. Okay, so if you don't remember, this was a graph of an ellipse. It's in the standard form. And if we graph this, the center is 0, 0, or HK is 0, 0. My a value, a squared, is 9. And a is equal then to 3. My b squared value is b is the smaller for ellipse, was 4, and so b is 2. So it's elongated with the y-axis because the bigger number is underneath the y value here in standard form. So we're going to go from the center up 3 units and down 3 units. We have points on our major axis, and then we're going to go to the left and right 2 units, points on our minor axis. You don't really need to know this terminology, but you should know it. And we have our ellipse here. So if I want to differentiate this, right now, all we know how to do is when it's in explicit form. And so let's first put that in an explicit form, and then let's talk about differentiating that using the implicit form. So explicit form, so let's put that equation in explicit form. So we need to solve for one variable in terms of the other. Let's solve for y. And so solving for y, let's first clear our fractions, and we can do that by multiplying through by our LCD of the denominator, which in this case for 9, the LCD would be 36, least common denominator. So let's multiply both sides of our equation by 36, and we can do that. And so if we distribute 36 times x squared over 4, that's going to give us, well, 4 goes into 36 9 times, so 9x squared, plus 36 times y squared over 9, 9 goes into 36 4 times, so 4y squared equals 36. We're trying to solve for y, so we're going to subtract 9x squared on both sides, trying to isolate the term with y. So we get 4y squared is 36 minus 9x squared. Now we want to get rid of the 4 in front of the y squared. So let's divide every single term by 4. And so we would get y squared is equal to, well, 36 divided by 4 is 9 minus 9/4 x squared. But we want y equals, and so in order to get y equals, let's take the square root of both sides. But recall, when you take the square root of both sides, on the one side, we put a plus or minus. So this is y is equal to plus or minus the square root of 9 minus 9/4 x squared. Because there's a difference between each piece, each term underneath that radical, and even though they're both perfect squares, because we are subtracting, there's more than one term, we cannot pull that out of the radical. I could actually factor out a 9 and pull that out, but let's not worry about that for now. So now it's in the form that we can take the derivative of this. So let's look at that. So let's, and this was put in explicit form. And then find the derivative. So let's just say dy dx. So we actually have 2 separate equations, right? One piece is above the x-axis, and that would be y is equal to the positive, the square root of 9 minus 9/4 x squared. And then the other piece is below the x-axis, and that would be y is equal to the negative of the square root of 9 minus 9/4 x squared. So if you take the derivative of the first one, we know that the derivative of the second one is just the opposite sign of that. And so let's just take the derivative of the first one, but before we can take the derivative of that, we want to rewrite that so that we don't have that radical there. And so let's do that. We can rewrite it. We can rewrite radicals without the radicals and with exponents instead. So this is raised to the 1/2 power. So taking the derivative of this, we need to use the chain rule. So the chain rule, we're looking at our outer function. The outer function in this case is some function raised to the 1/2 power. So let's take the derivative of the outer. So the derivative of the outer, I'm just using the general power rule. I'm taking my exponent, I'm bringing it down front of the inner function, so nothing changes inside the parentheses, 9 minus 9 fourths x squared. Subtract 1 from my exponent, 1/2. So 1/2 minus 1, or 1/2 minus 2/2 is -1/2. And this is where you need to remember that we're taking the derivative of the inside. So a lot of times, maybe just writing that you're doing that ddx of the inside, 9 minus 9 fourths x squared. The derivative of y is 1 dy dx. Dy dx there. Okay, so let's clean it up a little bit. And take the derivative of the inside because we haven't done that yet. So, and let's rewrite this. -1/2 power, we can bring that down to the denominator to make that a positive exponent. So we have dy dx is equal to, we'll have 1 here, all over, bringing this down, I would have 9 minus 9 fourths x squared to the +1/2, but I'm going to rewrite that as my radical, times the derivative of the inside. Well, the derivative of our constant 9, that's just 0, minus, so -1, times 9 fourths, times the derivative of x squared. So bring our power down front, times 2, x, subtract 1 from our power. So that's just a 1. So we found the derivative of this function, dy dx, is equal to negative, I really don't like, well, let's first do this too. I really don't like that I have a fraction within the fraction, so I would probably pull that 9 fourths out, but I also noticed that 2 and the 4, we can simplify, right? So 2 goes into itself once and this twice. So let's pull this 1/2 right here, -1/2 out front. Negative, so I'd have the 9 left, and I would have this x left. All over, I'm putting the 2 in the denominator, square root of 9 minus 9 fourths x squared. So that was for the positive, but we know the derivative of this negative would just change the sign here. So we know that plus or minus this was equal to the derivative. So in this case, this one would have been the negative, this one would be the plus. Okay, so we found the derivative. Now we could basically, if we wanted to find the slope, right, anywhere on this, we would have to look at values in our domain. So if I wanted to see what's happening at x equals 1, so find the slope of the tangent line, or the slope at x equals 1. So notice, because of our function, we're going to have 2 different slopes, which makes sense, right? We would have one above the x-axis, and if we look at that slope at 1, notice that that tangent line is decreasing. And if we looked below the x-axis at x equals 1, that point on the line, and we looked at it, that would be increasing, the slope of the tangent line. And so it makes sense that we have plus or minus in here. And I said the one that was on top was the negative. We found that was the negative one. And notice that the slope on that tangent line is decreasing. So that kind of makes sense with everything that we're learning. And so I could just find that slope by plugging it in. So dy dx, like another way to write this. Do a vertical line, x equals 1. So I'm rewriting in here, wherever I see an x, I'm going to replace it with 1. And so I would get plus or minus 9 times 1, so that's 9, all over 2 square root of 9 minus, well, 1 squared is 1, so minus 9/4. I would definitely clean that up a little bit. And let me just do that on the side for a minute, and then we can bring it down. So 9 divided by 2 square root of 9 minus 9/4. I need a common denominator underneath that radical, which is 4. So I'm going to rewrite my 9, multiplying it by 4 over 4 is 36/4. So I have 9 all over the square root. Well, 36/4 minus 9/4. That's going to give us a 27 all over 4. Remember, we can take the square root of the numerator and the square root of the denominator if we have a single fraction. So this is really 9 all over 2 square roots of 27, which I know is 9 times 3, all over square root of 4, which I know is 2. That 2's are going to cancel. And I know I can pull out the square root of 9 in that denominator. So here we would have 9, square root of 9 is 3 root 3. Notice here that the 3 goes into this 9 3 times. I usually don't like radicals in the denominator, but and we could technically really fast get rid of that by multiplying by root 3 over root 3. So this would give me 3 root 3 over 3. 3's cancel, and that's root 3. But we're not really concentrating on that piece of the math right now. And so, but let's just do it since we did. This whole thing, side work we got is root 3. So this is equal to plus or minus square root of 3. Okay, so let's talk about how we would do this using implicit differentiation. So let's say we didn't want to solve for y, or we didn't know how to solve for y, or it was impossible to solve for y with the implicit equation that we were given. And so we want to go forth and we want to try to take the derivative of this using implicit differentiation. The only thing that you have to be careful of is when we take the derivative of y, because y technically is a function of x. So, right, y can be rewritten as f of x. And so for some reason, let's say we had y squared here, and we wanted to take the derivative of y squared. Well, this right here, we can think of as f of x quantity squared. And so if we took the derivative, so we can write this as ddx of y squared. Another way to write that, I'm just going to write it with notation for now. Let me just pull this over. So ddx, same thing as the notation as this way, f of x quantity squared. So let's look at the right-hand side. Here, notice we need to use the chain rule. And so when we're taking the derivative of this y on the one side, we have to use the chain rule. And so we're going to be bringing our power down front. So 2 all times our inside function, f of x. Subtract 1 from our exponent, so it's 1, times the derivative of the inside. And the derivative of the inside we would write as, we can write as f prime of x. So another way to write this other side of the equation, dx of y squared is equal to 2. Remember, this is another way of f of x is another way to say y times y. Another way to say f prime of x is dy dx. So the whole point of that is when we're taking the derivative and it's in terms with y, we need to use the chain rule. So when we take the derivative of an implicit equation, make sure you put dy dx or f prime after the derivative. And again, that has to do with the chain rule. We're taking that function, that y value is a function of the x, and we have to apply the chain rule. So we have to take the derivative of the inside, multiplying by the end of the derivative of the inside. Okay, so let's look at that equation that we were just looking at and did it. We wrote it in an explicit form and took the derivative. So looking at that equation, we had y, what was it? It was actually x squared over 4 plus y squared over 9 equals 1. So we're going to find the derivative using implicit differentiation. So all we're doing is we're taking the derivative of both sides of our equation. So if we do something to one side of the equation, dx of one side, and I normally won't write it out this much in the future, but of x squared all over 4 plus y squared all over 9 is equal to the derivative of the other side, ddx of 1. So looking at the left-hand side, I would look at what types of rules I would need to use, and I just have a sum there, so I don't have to use any product rule or any quotient rule. I can think of this as, I need to take the derivative ddx of the first piece, and we can think of that, if it helps you, as 1/4 x squared, plus the derivative of the second piece, ddx of, we can pull out and think of this as 1/9 times y squared, if that helps you, equals, well, the derivative of the right-hand side, the derivative of constant, that's just 0. And taking the derivative, so derivative of 1/4 x squared, so bring our power down front. So we have this 1/4 times 2. And then we have the x and subtract 1 from our power, so that's 1. So this is where we have to be careful. So y is in function of the x, so we need to use the chain rule. And so we're bringing our outer function, we're going to bring the 2 down. So we have the 1/9 times our exponent of 2. Y, subtract 1 from our exponent, so that's just 1, times the derivative of the inside. So we can write the derivative of the inside as dy dx. Is equal to 0. Okay, so we're almost there. Let's actually clean this up a little bit. So this is the same thing as, well, 2 goes into 4 twice. And so this would give us x over 2 plus 2y over 9 dy dx equals 0. Okay. But that doesn't look like anything we did before, right? I can pull it back up. What did we get before? Let me just pause for a sec. And then let's show that they actually are the same thing. Okay, so I pulled over what we found the derivative was when we used it in explicit form. And that was when we solved for y, we got that equation. So let's show that these two things are equivalent. So before we can do that, and this is what we're normally gonna a lot of times want to do when we're using implicit differentiation. Once we did implicit differentiation, you want to solve for solve for dy dx. So let's do that with that equation that we got right here. So we want to isolate the term with dy dx, and then we want to get everything else on the other side. And so we would first subtract our x over 2. And so subtracting x over 2, we get this 2y over 9 dy dx is equal to, well, we subtract x over 2 on both sides and taking it from 0, so we get minus x over 2. Let's get rid of the fraction in front of dy dx so we can get that by itself. So instead of dividing by a fraction, we can think of it as multiplying by the reciprocal. So 9 over 2y to make that a 1. 9 over 2y. And so we get our derivative, dy dx, is equal to negative x, 9 times x. So let's put the 9 first. Negative 9x all over 2 times 2y, 4y. So notice this still is not exactly the same thing as this right here. But that's because our equation has y in it still. And so if we go back in there and we replace what y is with what we have over here, notice we're going to get the exact same thing. Where did this didn't have a 4? So I'm just looking at, did I do something? Oh, right here. No. So I'm looking at it and I'm just noticing that it's a little off. We should get the same exact thing. Plugging in dy dx. So I have to go back and look at it. Minus 9x all over 4 times, but y is plus or minus the square root of 9 minus 9/4 x squared. This plus or minus I can pull out, which makes this plus or minus here. So we're almost exactly the same. I need to click and find my error really quickly. Okay, we found it. It had to be right here. This 1/2 when we did our bringing down our power, I dropped it when I brought down the rest of the piece. So we needed to put that 1/2 in here, which if we brought it down, that and this in here had canceled as a 2. So where did it go? So this would actually, this was the dy dx. We needed that to be a 4. So So the 1/2 from out front, and then I had the 1/2 left over when I took the derivative of the inside. And so that gave me the 1/4, which is then makes these equivalent, which we want. Okay, so a lot faster, and a lot of times you don't have to solve for y. So you can, when you use implicit differentiation, you just leave it in terms of both x and y. Okay, so we're given the example. We have a quantity 3xy plus 7, and then that quantity is squared. And then it's equal to 6y. And it tells us that we want to use implicit differentiation. And then we're going to, once we do that, we want to solve for dy dx. So the only thing that we have to worry about when we're taking, using implicit differentiation is when we take the derivative of y, remember to tack on the dy dx after it. And so looking at this, I'm looking at the left-hand side of this equation, and I want to take the derivative. I notice that there's multiple rules I'm going to have to use, right? I have this quantity squared here, so I could either FOIL this out, which I don't want to, or I can use the chain rule. So I'm going to need to use the chain rule. And then when we get inside, notice I'm going to have to use, we have 3x times y. So inside, when we take the derivative of the inside, I'm going to have to use my product rule plus the sum. That one's pretty easy. And then, so let's look at that. And so this is where, because we're using so many different rules, sometimes writing out that I'm going to have to take the derivative, not taking the derivative is helpful. So let's use a chain rule. So the chain rule says we're going to bring our power down front. Don't mind that's up. We're going to bring our power down front all times 3xy plus 7. Subtract 1 from our power. So that's just going to give us 1 times the derivative of the inside. So d dx of 3xy plus 7 equals the derivative of 6y. Well, the derivative of 6y, we can do that. That's pretty easy. That's just 6 times derivative of y is 1, but then dy dx, because that was in terms of y there. So let's go and look at the following. So let's maybe distribute that 2 inside here. And so this gives me parentheses 6xy plus 14 times the derivative of the inside. So derivative of the inside says I have to use that product rule for the 3xy. So that would be derivative of the first, d dx of 3x. And then times y plus the first, 3x, times the derivative, d dx, of the second, which is y, plus the derivative of 7, so plus 0, equals 6. Let me put this in different colors, dy dx. So let's keep that parentheses, I'll leave it alone. So we have the 6xy plus 14. And now let's look at the derivative using that quotient rule. We have the derivative of the first piece, 3x. That's just 3. That's just 3 times y plus 3x times the derivative of y. So the derivative of y is 1, but it's in terms of y, so dy dx. Close this off, equals 6 dy dx. Okay, so we want to find dy dx. So we need to use some algebra and manipulate this to get dy dx all by itself on one side of the equation and everything else on the other side. I'm trying to think if there's an easy way to do this. Because of this multiplication here, it looks like we are going to have to distribute this out. Okay, so we can do that. It's not bad. But let's do it. So 6xy times 3y. So this, if I distribute this, 6 times 3, so this is 18xy squared. 6xy times 3x dy dx. So 6 times 3, that's going to be plus 18x squared y, and then I have a dy dx. Now let's distribute the 14. So distributing this 14, I have 14 times 3 is 42. And then I have a y. And then I have 14 times this 3x dy dx. So 14 times 3, that's 42. So plus 42x dy dx equals 6 dy dx. So we want all the terms that have a dy dx on one side of the equation and all the terms that don't have a dy dx on the other side of the equation. And so let's, since we have on the right-hand side just one term with dy dx, let's move these terms on the left-hand side over to the right. So on the left, we're going to keep the ones that don't have the dy dx. So we have 18x squared y plus 42y is equal to 6 dy dx. I'm subtracting to get it to the other side, so minus 18x squared y dy dx minus 42x dy dx. So once you've isolated all the terms on one side of the equation that have the dy dx, we're just going to factor that out. So the trick is to factor that out of all the terms. So I have to write down the other side still. 18x squared y plus 42y is equal to, pulling out dy dx from all the terms on the other side, we have times 6 minus 18x squared y minus 42x. And then now we can get dy dx by dividing both sides by what's inside that parentheses. And we got our equation. So we found the derivative dy dx is equal to, is there anything that we can factor out that would cancel? Those are all divisible by 6, it looks like. So let's pull out a 6. If I pull 6 out of 18x squared y, that is 3x squared y. I guess I could pull out a y there too, but it's not going to help me cancel with anything on the bottom. 6 goes into 42y, so that's plus 7y. All over, let's pull out a 6 on the bottom. So 6 goes into 6 one time, minus 3x squared y minus 7x. So those 6's cancel. And I'm just going to erase it so I don't have to rewrite it. And I guess just me writing this, I could have rewritten the whole thing. So just factor out and cancels A6. Okay, so let's look at an example. Again, we're using implicit differentiation to find the derivative of xy equals cotangent of xy. I just put in here, just as a reminder, what the derivative of cotangent x was. Dy dx would be negative cosecant x cotangent x. So looking at this, when we're looking at taking the derivative of both sides of this equation, this left-hand side, x times y, we're going to need to use the product rule. So let's just write out the product rule. So the product rule says take the derivative, d dx, of the first, which is x, times the second, which is y, plus the first, x, times the derivative of the second, so d dx of y, equals the derivative of cotangent, d dx of cotangent of xy. Okay, so let's look on the left-hand side and let's go through and take the derivative of the piece that we need to and keep the other piece the same. So the derivative of x with respect to x is 1. So we have 1 times y plus x, and the derivative of y with respect to x is 1. But y is some function of x. So we have to take the derivative of that inside. So times f prime of x, or dy dx. Equals, we need to use the chain rule here because this is not a single argument in here, it's x times y. And so let's look at the derivative of cotangent. So that is the derivative of the outer, which we said was negative cosecant of the inner, which was xy, cotangent of the inner, xy, times, you need to look at the derivative of the inside. So d dx of the inside, xy. So we're not quite done yet. Notice that, so we didn't even take the derivative of the inside here. But notice when we take the derivative of this inside, we're going to have to use the product rule again. So this would give us y plus x dy dx. Well, notice, isn't that the same thing we just took the derivative on this side? So we actually kind of did that work. So this is equal to this negative cosecant xy, cotangent xy, times the derivative of this, we just did the work, times y plus x dy dx. That was the product rule of xy. So we need to distribute, we need to get all the terms with dy dx on one side. And notice this is like two separate terms. So we want to distribute this negative cosecant xy, cotangent xy to each term in here. So let's bring down the left-hand side, y plus x dy dx is equal to, it's just messy because it's a lot, and I'm going to put the y out front. So this is negative y cosecant xy, cotangent xy, plus, now distributing it to this next piece, I have x. And actually this is negative, so let's just change our sign out here to be in minus. X, and then we have the cosecant xy, cotangent xy, dy dx. So we want all the terms, any term that has a dy dx on one side of the equation. Any term that does not have dy dx, we want on the other side of the equation. So it really doesn't matter. Maybe let's keep it on the left-hand side. So that would mean that I'd have to move over this y. So I'd subtract y on both sides. And I'd have to move this over. So I would be adding that to both sides. So let's do that, rewriting it. So I have this x dy dx. Technically, we're doing that so we can pull out the dy dx. Plus, getting this over there, x cosecant xy times cotangent xy dy dx. Is equal to, so we have subtracting y on both sides, so negative y minus this piece, y cosecant xy cotangent xy. Actually, look at this. So let's pull out dy dx. At the same time, let's pull out also x. We'll divide with that x to keep the dy dx by itself. And then on the right-hand side, notice you have a y here. Let's pull out actually a negative y. Okay, so if I pull out, I'm going to write it like this, dy dx x from this left-hand side, I would be left with just a 1 here, plus pulling out the x here and the dy dx, I'm left with cosecant xy, cotangent xy, equals, pulling out the negative y there. Notice we have positive 1 plus, pulled this out, so we're just left with cosecant xy, cotangent xy. So to get dy dx by itself, notice we're just going to divide through by this. If we divide through by this, notice what's inside my parentheses is the same. And so those are going to actually cancel. And all we would be left with would be this negative y here and this x here. So we could write it out. It's just that it's a lot messier. Let me just do it. But dy dx, I'm trying to skip steps, and I know that that's not great. And I try to get you guys not to skip some steps. And then I'm trying to do it. Okay, so I'm just rewriting what I have on the right-hand side of the equation. I'm dividing both sides by this x, and then this 1 plus cosecant xy, cotangent xy. Those parentheses cancel out with one another. And we're left with dy dx is equal to negative y over x. And that was the derivative of this xy equals cotangent xy. Okay, so we're going to find the second derivative of x squared plus y squared equals 1, the unit circle. And it tells us they want us to use implicit differentiation, and our solution is only in terms of x and y. So let's go through here. Let's take the derivative of both sides. Well, the derivative of x squared, that's pretty easy, 2x, plus the derivative of y squared. Well, that's just 2y. But that, again, it was y is in terms of x. We have to tack on the derivative of the inside, dy dx, equals the derivative of 1, which is 0. So I took the derivative of both sides, and I can go ahead and take the derivative again, or I can solve for dy dx first, and then go ahead and take the derivative. I think it's going to be easier if we take the derivative now. If I took the derivative after solving for dy dx, I would have an equation, I would have a quotient. And so I'm thinking let's take the derivative again. So if I take now the derivative of both sides, so the derivative of 2x, that is just 2. And it was in terms of x, so I don't have to worry about it. The derivative of 2y, though, that is 2 times 1. And then dy dx. Actually, let's talk about this. Dy dx. This here, though, is a product. So it's times this dy dx. And then we have this plus our 2y. Is that right? I'm not sure if I'm doing this right. Times the derivative, well, the derivative, this is of dy dx, is our second derivative. So d squared y dx squared is equal to, the derivative of 0 is still 0. So here we have, let's get the dy squared x by itself. And so here we can pull that out, and we can move this 2 to the other side. So let's subtract 2 on both sides. I notice this has a 2, and I notice a dy squared dx squared in both pieces. And so let's factor out the 2. Let's pull out the d squared y dx squared. If I do that, I'm left with this piece, just a 1. Plus, and I'm left with this piece, I'm just left with a y. So now if we divide both sides by this 2 bracket 1 plus y, these 2's would cancel, and I would get my second derivative of y with respect to x is equal to -1 all over 1 plus y. Okay, so I wanted to go back and talk about what I did wrong because it was a big, big no-no. And I should have, and I was a little worried about it, and that's why I wanted to go back and check the back of the book. So let's go right here where we took the derivative. And I said, let's factor out d squared y dx squared. This right here is not the same thing. This, let's bring down our 2 plus 2. This is the same thing as the derivative dy dx. That quantity squared. It's not the same thing as the second derivative. Plus 2y d squared y dx squared equals 1. So I want to solve for the second derivative. I'm trying to solve for the second derivative. I would isolate this piece. So let's subtract these and get those on the other side. We get 2y, the double derivative of y with respect to x, is equal to, so let's subtract this. I get -2 minus 2, the double derivative, or not the double derivative, dy dx quantity squared. So let's factor out a -2 on this side. That would give me 1 minus dy dx quantity squared all over. So we're going to get this double derivative by itself. We have to divide by 2y all over 2y. So the double derivative of y with respect to x is equal to this. Our 2's cancel. So we're almost there. The equation, though, was this double derivative. Probably easier to write y double prime. So we need to show that what we have, y double prime here, is equal to 1 minus, this is y prime quantity squared all over y. So let's look at that. I need to know what my derivative is. I took my derivative. My first derivative was right here. So my first derivative, let's do this on the other side. I had 2x plus 2y times dy dx is equal to 0. So if I subtracted 2x on both sides, divide by 2y on both sides, I would get dy dx. The first derivative is equal to -x over y. So another way to say this is y prime is equal to -x over y. So I need to go in there and I need to go back in and plug in what y prime is. And I'm trying to show you that it's equivalent to what the back of the book did, and they used the quotient rule. So I have y double prime is equal to 1 minus -x over y quantity squared all over y. So this is equal to 1 minus x squared over y squared all over y. Let's clear the complex fraction by multiplying by a fancy 1. How about y squared over y squared? So doing this, we get the second derivative is equal to y squared minus x squared all over y times y squared, which is y cubed, And if you look at the back of the textbook, and I probably dropped my negative. Did I drop my negative? I'm off by a negative. Let me find it. Okay. Here's my negative I lost. Let's distribute that negative. So this is negative now 1 plus negative 1 plus negative y squared maybe I just copied it down from the back of the book, so let me look at that too. Okay, so when I pulled out my negative sign, this needs to change to a plus. Plus. When I distribute that negative sign, that changes this to a minus, which makes this a minus, which keeps this as a minus, which is the same thing as this. Okay, so you could do it two different ways. You can find use implicit differentiation to take the derivative of both sides. You have to take the second derivative. You can then again apply implicit differentiation on both sides of the equation, or you could have, after you took the derivative the first time, solve for your derivative function and then take the derivative of both sides. The thing is, you're still going to have to go back in and do some substitution. So let me maybe go through this one problem, doing it using the quotient rule here. I'm going to stop the video and I'm going to restart the video with this example.